All right, welcome to the Explainer. Today, we're going to decode the invisible magnetic forces that literally shape our universe. From the tiny spinning atoms inside your computer to those massive swirling galaxies in deep space, magnetism is absolutely everywhere. So we're going to break down exactly how this fundamental force interacts with matter. Let's get right into it. So picture this. It's a classic thought experiment. If you have a typical bar magnet and you just snap it right down the middle, do you finally get a purely north piece and a purely south piece? Okay, let's dive into this. Because the answer is a resounding no. There is no way to do it. Cutting a magnet never ever isolates a single pole. Instead, you instantly create two smaller, perfectly functioning magnets, and each one has its very own north and south pole. Here is our roadmap to master all of this today. 1. Bar magnets and field lines. 2. The solenoid equivalence. 3. Decoding Earth's magnetism. 4. The three magnetic elements. And 5. Classification of magnetic materials.
Section 1. Bar magnets and field lines.
In classical physics, we model a bar magnet as a magnetic dipole. And that really just means it's an arrangement of two unlike poles, north and south, of equal strength, separated by a tiny distance. Now, the spatial orientation of this dipole is defined by something we call the magnetic dipole moment. That's represented by the vector m. You calculate it just by multiplying the pole strength, lowercase m, by the distance between them, 2L. Oh, and remember this key detail for sure. By convention, this magnetic moment vector always points from the south pole to the north pole inside the magnet. And this brilliantly illustrates what that invisible dipole is actually doing to the space around it. You know the drill, right? When you sprinkle iron filings around a bar magnet, they don't just sit there randomly. They actually align themselves into this beautiful, distinct pattern. This physical response perfectly mimics what the legendary physicist Michael Faraday conceptualized as magnetic field lines.
Now, Faraday's whole visual tool here, it operates on some pretty strict mathematical rules. First off, unlike electric field lines, magnetic field lines always form continuous closed loops. They emerge from the North Pole and enter the South Pole externally, but then they just keep going south to north internally. Second, a tangent drawn anywhere on these lines gives you the exact direction of the net magnetic field. Third, and this is crucial, these lines can never ever intersect. If they did, it would mean the magnetic field has two directions at once at that spot, which is just physically impossible. Finally, where the lines are really densely packed together, the magnetic field is at its strongest, like right at the poles. So, because these lines form unbroken loops, any closed surface is going to have an equal amount of magnetic flux entering and exiting. This is Gauss's law of magnetism, and it dictates that the net magnetic flux through any closed surface is exactly zero.
Section 2. The solenoid equivalence. So, think about a solenoid, just a cylindrical coil of wire carrying an electric current. If you observe the magnetic field produced by this current-carrying finite solenoid from a distance, it is virtually indistinguishable from the field of a standard bar magnet. The macroscopic transport of electric currents flowing in loops through that coil generates field geometry that perfectly mimics the aligned atomic scale magnetic domains of a solid magnet. It's kind of a major physics plot twist. But here's the catch. While their fields might look identical, their actual properties are drastically different. A bar magnet is a permanent magnet. Its field strength is fixed and its poles are permanently set in stone. Literally. A solenoid, however, is an electromagnet, and that gives us immense control. We can crank up its strength by simply turning up the current, or just adding more turns of wire. We can even instantly swap its north and south poles just by reversing the direction of the current. This equivalence, and the control it gives us, is exactly the fundamental principle we use to build powerful technologies today, from the motors in your kitchen appliances to giant MRI machines and frictionless maglev trains.
Section 3. Decoding Earth's magnetism.
Okay, first things first, we need an explicit myth buster. You might have seen diagrams showing a giant iron bar magnet buried deep inside the Earth. That is completely false. The interior core of the Earth exceeds 3,000 Kelvin. That is way too hot for iron to hold a permanent magnetic field. It's essentially just a chaotic, sloshing ocean of liquid metal down there. Instead, modern geophysics points to the convective dynamo theory. It's actually the churning, circulating currents of molten metals in the Earth's outer core that generate our planet's magnetic field. Now, what's really interesting about this alignment is that while the molten core generates a field acting largely like a giant dipole, this magnetic dipole is not perfectly aligned with how the Earth physically spins. The axis of the magnetic dipole is actually tilted at roughly 11.3 degrees relative to the Earth's geographic rotational axis, which means true geographic north and magnetic north are definitely not in the exact same location.
Which actually brings us to a really fun question. We know a compass needle aligns with magnetic field lines, right? So what happens if you hold a standard horizontal compass exactly at the magnetic north or south pole? Well, because those magnetic field lines are diving vertically, straight down into the Earth or straight up, the horizontal component of the field just drops to zero. Your compass needle would experience no horizontal force at all, rendering it totally useless. It could just point in any arbitrary direction.
Section 4. The three magnetic elements. So to actually pin down the Earth's vector magnetic field at any specific location on the surface, you must measure three independent quantities. Geologists call these the magnetic elements of the Earth. And they are 1. The magnetic declination, 2. The angle of dip or inclination, and 3. The horizontal component. Let's quickly walk through the geometry of this. First up is magnetic declination. Because the magnetic poles and geographic poles are offset like we talked about, declination is simply the angle between true geographic north and the magnetic north your compass is actually pointing to. Second is the angle of dip. Imagine if you could let a compass needle freely point up and down. This is the angle the total magnetic field makes with the horizontal surface of the Earth. Finally, we have the horizontal component, and this is exactly what it sounds like. It's the projection of that total, tilted magnetic field acting purely along the horizontal plane. By knowing just these three elements, you can map the exact magnetic environment literally anywhere on the globe.
Section 5. Classification of magnetic materials.
Let's move to and see how this builds all the way down at the atomic level, looking at how different materials react to these fields. We'll do a rapid-fire sequence of the three main classifications, starting with diamagnetism. Diamagnetic materials like bismuth, copper, and even water are actually weakly repelled by a magnet. In fact, because water is diamagnetic, physicists have actually used ultra-powerful magnets to levitate live frogs. This happens because their atoms have no permanent magnetic moment of their own, so when they're exposed to an external field, they develop this tiny opposing field. And interestingly enough, this weak repulsion is completely independent of temperature. Next up, contrast that with paramagnetism. Materials like aluminum and sodium have atoms that do possess permanent magnetic moments. When you apply an external field, these tiny atomic magnets try to line up with it, and that results in a weak attraction. However, they are constantly fighting against the chaotic thermal motion of their own atoms. So as temperature rises, this thermal scrambling increases, and the material's magnetic susceptibility falls. That inverse relationship is mathematically described by Curie's law. And then, of course, we have the heavy hitters, ferromagnetism. This includes materials like iron, cobalt, and nickel. These materials are strongly attracted to magnets. Their internal atoms not only have permanent moments, but they actually cooperate. They lock together into these highly aligned groups called magnetic domains. This allows them to become powerfully magnetized and retain that memory, essentially becoming permanent magnets themselves. But, and this is a big but, if you heat a ferromagnet up high enough, past a specific point called its Curie temperature, that intense thermal energy literally destroys the domain structure. Actually, scratch that. It doesn't just destroy it. The material abruptly becomes merely paramagnetic. To lock all this in for your exam prep, or honestly just for great cognitive retention, here is a concise summary of the 3 M's of magnetism. Diamagnetic materials are weakly repelled, and they are totally independent of temperature. Paramagnetic materials are weakly attracted, but remember that attraction decreases as temperature goes up. And ferromagnetic materials are strongly, massively attracted, forming those permanent domains, right up until they are heated above their specific Curie temperature. Which brings us to a final, kind of profound thought. We have explored magnetism today from the tiny atomic domains of iron all the way to the molten dynamo core of our entire planet. And yet, through all of this, and despite billions of years of cosmic history, no one has ever observed an isolated magnetic monopole. Not once. The universe, it seems, just absolutely insists on balance. Magnetic fields always form continuous, unbroken loops, binding together everything from the smallest electron to the vastness of the Earth itself. It really leaves you wondering, what other invisible symmetries are out there just waiting to be mapped? Thanks for learning with us today.